Okay, let's get started. Okay, this week, we will continue to talk about new I/O devices. Okay, today we want to finish. Which one? We want to finish these two, UART and timers. Right. So if you recall what we have done so far, we discussed two I/O devices. The most simple I/O device called GPIO, right? Inside computer system, inside the embedded system, hardware system, embedded Zinc, right? Inside Zinc 7000. This one is called, system on chip. You have ARM CPU. Okay. Then many different I/O devices. So inside the PL, we instantiated GPIO, right? GPIO, and also we used I2C I/O controller to connect what? To connect motion sensor, right? Or accelerometer, right? So if you think about industrial control system, right? Industrial control system, you are attaching sensors and actuators, and those are I/O devices, sensors and actuators, right? So you have sensors, right? Some sensors and actuators. Those are I/O devices, and we call these, I/O devices as well, right? There is I/O device, I/O devices, right? And this one is I/O devices also. It's confusing, right? So inside the chip, GPIO is I/O device. This I/O device is controlling this I/O device. So in this case, you can think of it as I/O controller, I/O controller, right? That is actual I/O device. You are controlling these sensors and actuators through this, GPIO. So by accessing, using software, you are accessing, registers, okay, reading and writing. Then you can turn on some, LEDs, and you can take input from, sensor. So you can think of it as I/O controller, GPIO. Same thing goes to I2C, right? I2C itself is not doing anything useful, right? You need to connect, actual I/O device, accelerometer, motion sensor, right? And using this I2C controller, you are accessing, you are, controlling this, motion sensor. This one is actual I/O device, right? That is controller, I/O controller. And this week we will talk about UART and timer, right? So in case of timer, you are not connecting anything. Timer itself is I/O device. It is I/O device. You are not connecting anything. You are just accessing, right? And UART, I would say UART is also I/O device, not controller, right? Even though you are connecting other entity, other computer, like notebook, okay, for communication. You want to talk to notebook, right? These two guys want to talk to each other through UART. But in this case, I would call this I/O device. So I'm trying to explain. Okay, I/O device. I/O device is connected through I/O device. It's a little bit strange. So you can call this I/O controller. Okay, let's talk about UART today. And timer is super simple. I think it takes only 20 minutes or so to discuss. So I think 1.5 classes we will focus on UART. Okay, let's talk about this. This one, Sawon, can you please?
Handling I/O devices in software. I/O devices typically provide three kinds of registers: configuration registers, data registers, and status registers. Software sets up I/O devices with configuration registers before normal operation. Status registers indicate status of I/O devices.
Okay, thanks. So when you study I/O device, you have to think about these three kinds of registers, right? In any I/O device, you need to set some configuration register, okay? And after that, you are accessing data registers. And during normal operation, a status register, indicate the status, as the name implies, the status of I/O device. Right? I/O device is working fine, or some abnormal event happened, that is indicated in status register. Okay, so in UART, same thing goes to UART, right? Configuration. Okay, before normal operation, you have to set operating condition. Okay, UART. What is operating condition in UART? The speed. The first one, we call that baud rate. How fast you want to communicate between these two, right? How fast? Something. The popular baud rate, 9600 bits per second. Every second, you want to send out, 9600 bits per second. The second is packet format. Oh, okay. So 9600 and 1152 BPS. These two are, very popular. Right? So you can set a baud rate either to this one or to this one. Okay. And packet format. How many bits do you want to send in one packet? Something like 8-bit, 7-bit, 6-bit, something like that. So you have to determine these two before normal operation, right? How fast you want to do communication and what is the packet format. So after that, normal operation, right? Through data register, you can send data to your notebook computer and you can receive from your notebook computer, right? And status register, we will talk about that. So software, using software, you set up operating condition, okay? Operating condition before normal operation, okay? So during normal operation, you use data registers, okay? I want to send out hello world message to, notebook computer, for example, right? Status register, okay? This one, Himin, can you please?
UART, Universal Asynchronous Receiver and Transmitter, used for serial communication. Simply called serial port, has a long history, still widely used in embedded systems designed for debugging purpose. Detected as a COM port in Windows. Its original shaped port has almost been disappeared in computers. Instead, the serial to USB is used whenever necessary.
Okay, thanks. I'm not sure how many of you, remember this, computer I/O port backside. So it is like 20 years old computer. I think Jinuk remember, right? Jinuk is old enough. Uh, and so Mingyu, you're not that old enough, right? Don't remember? Right. Do you understand? Do you know this IO port? Really? You are that old? So it is like you're 20 years old, right? 20 years. Let me zoom in. Okay, let me make it big. So here, that is called parallel port. We used to connect a printer, okay, printer through this parallel port, parallel, connector. And this one is VGA to connect monitor. And this one got replaced by now HDMI or display port, right? And this circle shaped connectors, those are used to connect keyboard and mouse. And that got replaced by USB also, right? And this one is a serial port that is used to communicate between computer. You can connect this computer to other computer through that connection. Okay, that is called 9-pin. Count how many pins? 1, 2, 3, 4, 5, and 4. So 9, right? 9-pin connector. So we used to connect 2 different computers through that serial port. Okay. So now almost everything got replaced by USB, right? So here, so ordinal shape almost been disappeared in computer. Instead, we use USB. Okay. And UART has a very long history. USB has, serial port has a very long history. It first appeared in early 1970s. So 50 years old, right? 50 years old device, but it is still very widely used, really very widely used IO device. Think about embedded system. In embedded system, any kinds of embedded system, hardware system, you have at least 3 IO devices: GPIO, we studied, and UART and timer. Those are essential, almost essential IO devices. So that is still very widely used. Okay, and the name acronym is universal asynchronous receiver and transmitter. So receiver and transmitter, that terminology is okay, but how about asynchronous? So if you have term asynchronous, that means there is no clock involved. So here you are using only 2 wires, actually 2 essential wires. There is a TX and RX, TX and RX, okay, to talk to each other. So send something through that connector, okay, 1 wire, and receive some message through that wire. There is no clock signal, something like that. No clock signal between these 2. So no clock signal involved, then you call that asynchronous. Okay, asynchronous. In JetBot, you already, right? Second connection. So this one. Can you read the marking here? This one. Okay, there is a some marking called UART, right? So that connection is used for UART communication, and this connection is used to download hardware and software to the board, right? Through that connector, JTAG, hardware goes to Zynq, right? And software goes to this main memory, right? So that is serial communication. So we already, let me turn on this board. Then open device manager. Okay, check out this COM. So you have a COM4. So if I turn off that board, then that COM4 disappears, right? If I turn on, then computer recognizes that a serial to USB device, right? So COM4 that is used, for serial communication. COM4. Okay. Let's move on. Okay, the real stuff. This one, Mingyu, can you please?
UART controller in Zinc. It is a full duplex synchronous receiver and transmitter. Programmable baud rate generator. 64 bytes receive and transmit Fifos. Programmable protocol, 6, 7, or 8-bit data. Number of stop bits and optional parity set and interrupt generation.
Okay, okay. So the first bullet, what do you mean by? Mingyu, what? Turn off your microphone, please. So that is UART, right? And we have Zinc. So full duplex means you can send the message. Okay, you can send the message because you have two physical wires, right? TX and RX. So you can send some message, for example, hello world, hello. Then also at the same time you can receive message from other party, right? So that can happen at the same time. TX, RX. That is called full duplex. So if you have only one wire, then one at a time, right? Send or receive. Send or receive. That is called half duplex. Half duplex. But we have full, right? Full duplex, right? Meaning that you can send and receive at the same time because physically you have two wires, right? And programmable baud rate, right? That what does it mean? So that number, okay? You can set a communication speed, either this one or that one or other number if you want, right? And you have 64 byte FIFO, separate FIFO. That means in UART you have a buffer, 64 byte, 64 byte. This one is TX FIFO, okay, and RX FIFO, okay, 64 byte, okay. And programmable protocol. It is talking about packet format, programmable, okay. You can send 6-bit, 7-bit, or 8-bit in one packet, depending on your setting, configuration register setting. And also how many bits you want to use as a stop bit. So we will talk about that packet format, but in the packet format, you have to have a start bit, actual data, and stop bit. Start, data, and stop bit. So it is talking about that how many bits you want to use as a stop bit, and optional parity setting. Okay? Optional parity setting. And depending on your configuration register setting, you can also generate interrupt. Okay, why do you want to send it? Why do you want to use interrupt? Think about you are receiving something, receiving some message, then message arrives here, then you like UART to notify that event to CPU. CPU is doing something, some other work, right? Message receives, then let me know. Okay, I can do something. So interrupt generation. Okay, so let's talk about this. This one is packet format. Take a look at this. So second, packet format. Okay, so that is typical, packet format people use. Start with, and data 0 to data 7, 8-bit data. Okay, then optional parity bit. Optional. Okay, if you don't want parity, you can remove that, this one, and stop it. So let's. So we are going to, right? We are going to set up, right? We are going to set up this environment. What environment? Jinc and notebook computer. These two guys are talking to each other, right? So here we are going to write the software, our own UART software that is running on Jinc device, right? How about this notebook computer? You have to run some software, right? For that communication. So for the we don't want to write our own serial communication software, right? So instead, we will be using this one, Teratom. Okay, please download this one. And I already set up that environment. So here, Teratom. So that is the one we are going to use here. Click on setup. Setup. Then not on this program, right? Not only serial communication, but SSH and TCP/IP, right? These things supported. So serial port. So look at this. So we are going to use COM4, right? Because here we have COM4, right? We connected through that. So computer recognizes that connection as a COM4. So we will use COM4 and speed 1152. So you can select, right? 9600 or 1152. So or other some numbers if you want. Okay, but that is a widely used baud rate and data 8-bit. Okay, this one, right? So 8-bit data. Okay, we want to send 8-bit data in one packet. So that is the one. That is what means. And parity is optional. So we don't want to use parity, odd parity, even parity, and so on. None in this case. Okay, so we don't want to use the parity, and stop it 1 bit. Okay, that is the setting. Okay, so in on notebook computer or PC, Teratom is running, so it is ready to receive a message from Jinc, and you can also use your keyboard, right, notebook keyboard, and type some message, and that will be sent out through that connection. Okay, so here, okay, so that is the setup, right? You have a JetBoot and computer that is connected through USB, okay, USB, TX and RX, and this packet is running, okay, running from Jet to PC or PC to Jet. Okay. Okay, this one is the block diagram. Okay, so this orange box is Jinc. Okay, and you have notebook computer, and that is connected through USB. The important thing you have to look at is this internal block diagram. You have some control register, data register, status register, okay, living here. Okay, using those registers, you can set up operating condition, right? And data register, you can send the data. Okay. So the registers, the one you have to study. And to program these registers, we are using that connection called APB, Advanced Peripheral Bus. That is ARM proprietary protocol, the bus protocol. Okay, so bus protocol means you have address line, data line, some control line. CPU want to talk to that guy. CPU want to program, right, these registers through that connection, APB. So ARM's proprietary, ARM is providing that protocol, APB protocol, right? Because we are using ARM, right? You don't have any choice just to use, APB, right, to connect, this IO device. But APB, you have address, data, and control signals. What else? And UART is receiving some clock and reset and clock. Okay, reset and clock are default input signal in digital, any digital logic, right? So reset and clock, and it is generating interrupt. Okay, interrupt. We will talk about interrupt later on. Big picture first, and this one. Okay, so here. So some detailed internal block diagram. Again, you have UART here. Okay, UART, and PC is connected. And control status register, data register here, TX54, RX54. Okay, so if you send some message, if you write some message like hello, HELLO, like this, hello, to TX54, then each byte, data in each byte, right, that is 8-bit data. That is sent bit by bit through that wire. Okay. So if you program, okay, TX54, then transmitter will send bit by bit, okay, bit by bit of this 8-bit data. Okay. Okay, then what you have to do? First, what you have to do is we have to determine which baud rate we want to use and the packet format, okay, we want to use. Okay, so let's stick to 1152. That is very widely used. 1152. Then that is the formula. You have to use. Okay, this one, to generate that number. Okay, so from this input clock, okay, this one is important. From input clock, okay, let's go back to here. From this UART ref clock, UART reference clock, right? That is input. From this UART reference clock, we want to generate that number. Let me write down again. 1152 bits per second. So in other words, that is 1152 hertz. Okay. So let me draw clock. So that is 115200 hertz. Okay. So in one second, there are, within 1 second, there are how many? One pulse. There are 115200 pulses. That is the meaning of this number, right? So from this input clock, let me write down. From this input clock, there is a UART UART reference clock. From this input clock, you want to generate, internally generate. You want to internally generate 1152 hertz. Okay. Some hardware module. You have some hardware module that is taking this number, taking input, and generate this number. So UART reference in our Zinc system, that is 50 megahertz. 50 megahertz. So from this input clock, you want to generate this number. Okay. So using that formula. Okay. So take a look at this. Take a look at this block diagram. It's very simple. You have a multiplexer. Okay. So multiplexer selection is done through that register. UART mode register, bit 0. Depending on bit setting, you can select 50 megahertz or divided by 8 clock. Okay, that is the clock input, selection clock. Okay, hold on. What's happening? Someone is 농악대가 갑자기 난리를 치네. 해제돼갖고 오늘부터. Okay, so 50 megahertz, then you want to generate that number, right? So using that formula, selection clock, selected clock, okay, selected clock. So in our example code, we are going to use that UART reference, okay? And this multiplexer select the first one, okay? So selection clock, selected clock is equal to reference clock, so 50 megahertz, okay? CD, clock divider, okay? Clock divider, and you divide this output further by the BDIF like this. 2 division, right? CD divided by this number, and further divided by this number. Actually, actual number is BDIV plus 1. Okay. So somehow, right? 50 megahertz, then CD clock divider. Right? It is simple, right? Clock dividing clock and BDIV plus 1. So you want to get this one, 1152, this number, right? Hertz. Okay. So CD is provided CD can be programmed with that register, baud rate register, BDIF, baud rate generation register, baud rate divider register. So if you scroll it down, backup slide, sorry, control register, mode register, here, baud rate generation register. You have a CD. Okay, and next slide, I think, divider register, BDIF. Okay, BDIF. So using that register, you can program CD and BDIF. Okay, CD and BDIF. Okay, so UART reference, same slide. UART from reference, you determine baud rate. Okay, communication speed, and what is that baud sample, right? So you are tapping this line, right? You are tapping this line. So that clock is used to. So here you have 2, right? That clock is typically 16 times faster than actual baud rate. That is typical number. It doesn't have to be 16, but that is typically used, 16. So 16 times faster than this one. And that clock is used to, that clock is used to take input. Notebook is sending some message, right? You are supposed to extract data from this RX line, right? And when you extract the data from this RX, you are using that clock, okay, to get information like this. Both sample, that is typically 16 times. Look at this, 0 to 1 to 16, okay, or 0 to 15. So start bit, actual data, okay, start bit, actual data 1, and so bit by bit, right? So it is 16 times faster than internally. UART is taking samples at this rate. Okay, taking samples, rising edge of the clock, taking sample, second rising edge, taking sample, sample, and internally it is so trying to take the midpoint out of this 16 sample, then figure out, okay, this is the start bit. Okay, same thing goes to data 0, data 1, data 2, data 3 to figure out each bit. Okay, so again, the reason why you want to generate this one is to get data, to extract data from RX line. So how to data? By taking samples, right? You have a start bit and D0 and D1, taking samples like this, 16 samples, and you are trying to take a midpoint, okay, to figure out the start bit. So this one, let's read. Q1, can you please?
Overrate example. Values for CD and EDI is examples of system clock rate of UART clock equal 50 megahertz and UART reference clock divided by 8 equal 6.225 25 megahertz is assumed. The frequency of the UART reference clock can be changed to a more accurate overrated frequency. Refer to chapter 25, clocks for details to program the UART reference clock. Okay,
Thanks. So here from reference clock, right? Input clock, you want to achieve, for example, this speed, 1152, right? So CD. So then what number? CD and BDIV. Okay, what numbers these two should be? So that is an example, 62.004. And BDIV supposed to be 6 to get this exact, number. But you cannot program real number. Okay, that's supposed to be integer. This one, these two supposed to be integer, not real number, right? So instead of using 62.004, you have to use 62, closest number. 62 for CD and 6 for BDIV. Then actual baud rate you can get is this number, 1152, very close to 1152, but not exactly 1152. Okay, 1152, 7.37. Okay, so that means that if you set these two numbers, then you are setting that operating condition. Let's use that number. This one, BPS. Okay, but the problem is your notebook computer is not able to set this number, right? Notebook computer, you are setting UART with that number. Okay, So there's a difference, 1152.07, but 1152.00. Okay, so different communication speed. That means what? Different communication speed. Every once in a while, you are getting some problem. Okay, so you are not receiving or sending. You are not receiving your correct data every once in a while. That is error rate. Percent error rate. Okay, 0.0064% of the time you are getting some problem. Okay, because you cannot get that exact number. Okay, so you have to keep that in mind. In UART communication, there are some error rate. Okay, but not that often. Every once in a while. Okay. This slide is talking about how to create a reference clock. Reference clock is generated. UART input, right? This reference. Okay. So output is reference clock. This reference clock, and the input source is this PLL, IO, DDR. From this input clock, you can cook up. You can select your reference clock. Okay. But here you don't have to worry too much about this. Reference clock is 50 megahertz. Okay. And this one. Now we need to talk about the registers, control register, configuration register, data register, and status register. And this one, oh, okay. This one is talking about this clock selection. This clock selection, right? And this multiplexer is controlled by this one, source selection, and that is one, right? Source selection. Clock act 0, act 1. Anyway, right, there's the one. Clock selection. Okay. Yes, enabled and disabled stuff. And those are UART registers. The registers UART is providing, right? So I color coded. Okay, so the blue TX RX enable. So you can, if you categorize these registers into 3, right? Configuration register, data register, and status register. The first one, configuration register, right? TX RX enable, disable. Second is a packet format, right? So configuration register. Yellow is also part of configuration registers, right? Board setting. And green is data register. Okay, using TX5, RX5, you are sending data and receiving data. And the others are status register. Okay, so okay, let me show you example code and better to explain with examples, right? So here. So example code is here. First one is hello. This one. UART hello. Okay. So download it and create a project. I already did that for you. By the way, if you use, so I'm using this Plex experiment. The hardware platform you set up in the first lab. Okay, this hardware platform, and if you double click this, you have two UART, right? UART 0 and UART 1. And the first one is always enabled. So by default, right? So we are using UART 1. Okay, this is UART 1. Then check out this code. The first one is init, UART init. That is defined here, UART init. And init, right? As the name implies, initialization, right? Operating mode setup, right? So here, using this mode register, packet format, right? Packet format, normal mode, 1-bit stop it. Where is that? Mode register. You have here, right? Mode register. Okay. Second one. And using this mode register, look at this. Normal mode, right? Normal mode. Okay. And how many bit you want to use as a stop it? 1-bit stop it. Okay. And parity setting. Okay. We are not using parity, so no parity. So look at this number, 20. 20 means what? In binary, 0010, right? 0010. That means this one, 1. Right? Don't care. X means don't care, right? So 1, 0. Okay, no parity. And here, 0, right? So 8-bit, 8-bit data, and 0, the clock source. We are using reference clock, not divided by 8 clock, just reference clock. Right? So that is packet format. This one packet format. And using control register, you are doing what? Disable RX and TX first, because we are doing some configuration. Okay, so before you do configuration, you have to make sure, okay, disable RX TX communication. Then later on, you are enabling, right? So here, disable and enable. In between, you are setting up, baud rate. Okay, so there is a baud rate. So we are getting 50 megahertz clock, and using baud rate generation register. Where is that? Using baud rate generation register and divider register. Okay, that is here. Okay, using these two, okay, yellow registers, you are cooking up that number. But again, this one is not exactly same as this one. Our goal is to create 1152, but in reality, you are getting this number. That means you have some problem, right? Every once in a while. Okay, anyway, that is initialization. Okay, initialization. Then let's go back to this one. And here, branch and link. You are calling that function, okay, to send message. Check out this label. Okay, so branch and link. You are hello. So you are executing this one and come back. Okay, and calling that function again. So here, this function, the goal is to send out this hello world message, okay, to the PC. Okay, so let's analyze this one together. Okay, string, this label, the location of this label, right? So R1 contains the location of what? The first character. Okay, so in the status register, what is that? Status register. This one. Status register is read only, and that is what? That is doing what? Status register, right? So it is I copy and paste some important information from status register. So here, take a look at this. This bit. FIFO is full. FIFO is full or not? TX FIFO. This one, TX FIFO is empty or not? Okay, empty. That means what? We are talking about this TX FIFO. This TX FIFO is full or not, right? Or empty or not. And RX FIFO, right? RX FIFO, that FIFO. So okay, notebook, you are sending, many messages to, to Sync. Then eventually that will be, full. Right? So RX FIFO is full or empty. Okay. So those are important information. Okay. TX FIFO is full and RX FIFO is full or empty. Right? Full, empty. So we want to, using program, we want to check these bits. Okay. Let me make it small. So put this one too. Okay. So take a look at the code. So reading. So let's very small code. So we can analyze this code together. So R0 is what? R0. So reading from status register. Okay. So that status register. Okay. Then you are doing AND operation with 8. 8 means what? In binary 1 3 zeros. 1 3 zeros means TX empty. That bit 3. FIFO is empty or not? TX FIFO. Okay, this FIFO is empty or not? You want to check that status. Okay, TX FIFO is empty or not? This one, TX FIFO. If, okay, compare, right? You are doing AND operation to extract that information, bit 3, and compare that against this 8. Okay, not equal means what? Compare, it is setting flags, NGCV. So not equal, that means not equal. If it is 0 means not empty. Okay, not equal, then you keep looping this, right? You are waiting until TX FIFO is empty. This FIFO is empty. Okay, if it is empty, okay, 1 empty, then you fall through, execute this one. Okay, so R1, you are reading from this location, R1. R1 is this one, right? It's the location of string. The first character. First character will be loaded into R3 register. Okay. Then, R4 contains the address of TXRX FIFO, the location. So you want to write, first character to here. So what is the location, right? Location. Show you here. Location. We are using UART1 among these two, between these two, the second one, right? So location is E 3 zeros 1030. That is the location of this, TX FIFO. Okay. So the R4, okay, the location, okay. Then R3, the first character will be written to this TX FIFO. Okay. Then compare if R3, the character is equal to 00, meaning the last character. So you want to send the character, character by character until you hit, this the null 0. Okay. If equal, then equal, then you fall through, right? Fall through, return back, right? If not equal, then you TX loop, right? You keep executing this one until you send out, each and every, character until, 0A, 0D, 0A. Okay. So let me download it to the board and show you a demo. Okay, it's turned on. So here, pretty simple program. But if you are new to UART, if you haven't taken my undergraduate course, probably confusing, right? But it is not that hard. Okay. So initialization, right? So let's skip this part. Set breakpoint here. F8. Okay. Then remove breakpoint probably. Branch and branch. Okay. Then registers. Okay. R1. Okay. The location of the string. R1, the location of this hello world, right? It happens to be this number 100A14, right? And F5, status register R0. Okay, that is a status register location. Where is that? Status status register. Okay, 10 to C, right? 10 to C, right? UART1 status register. Then 5. Okay, so check out this one. Okay, now TX54 is empty. There is nothing in TX54. Okay, so you want to send out first character. Okay, H. So R3 contains 48. 48 is ASCII code. ASCII code for H, right? So 5 store byte. Then what would happen? If I press F5, then what would happen? R3 first character will be stored. Okay, first character will be stored in TX54. Then UART will take out that byte, send out bit by bit to your notebook computer. Okay, so here we are expecting some message H. H will appear, right? Your PC will receive that information and display the ASCII character, right? So let me press F5. H here, right? First character. Okay, then the data you sent out is not 00. Okay, 00, not 00, first character. So looping TX, right? Here, next character H. If I press F5, H, E, sorry, then HELLO, right? L word. Okay, then what is that? 0D, 0A, what is that? Check out ASCII table. Okay, ask table. Okay. So here 0D, 0D, 0A. Right? D hex, right? D carriage return. Next line, carriage return. Next line, A line feed, right? Next line and first column. Actually return, right? That is return. Right? So check out this cursor. Okay. Now 5. Okay. It goes back. Okay. Then next line. Okay. Like this 0D08. Then 00. Then return. Okay. Any question about this? So if I press forever, right? Branch forever. So it keeps. If I press F8, right? Then keep hello world message, right? Hello world. Stop it. Okay. Any question about this? Does it make sense or is a confusing point? Anything? Too simple? Too basic? So one thing suspicious, probably one thing suspicious is what? This TXRX54. Okay. TXRX54, I told you that is 64 byte inside, right? 64 byte. 64 byte for TX54. TX. Okay. And 64 byte for RX54. Okay. And one address. What address? That address, right? E30s. E30s. 1030 got assigned for both TX RX54. What does that mean? It sounds very strange, right? No? It sounds very strange, right? No or not? Is it or not? It's okay or not? At the beginning, if you take a look at that data sheet, right, it sounds very strange, right? Just one word location for TX54 and RX54, right? The first, how do you distinguish? How do you distinguish between these two? What do you mean by distinguish? CPU, right? Or so your software. Your software want to access this guy or that guy, right? How to make the decision? Right? So you are using the same location to access that guy and that guy. Then, so what does that mean, right? You are targeting that location. Then you are accessing that guy or this guy. That is differentiated by what? Store and load, store and LDR, store byte. Let me use that instruction. If you use store byte, then you are accessing, TX54 because you are, sending some message, right? You are writing some data, right? You are not writing data to RX54. RX FIFO is supposed to receive something, right? So if you use store instruction, then you are accessing TX FIFO, and if you use LDRP, then you are accessing RX FIFO. Okay. Then the second question is 64 byte, right? Then one location, 64 byte. It sounds very strange, right? Probably first location, let's say E30s 1030, and the last location, next location. If the spec says next location is 0E30s 1031, and the next location 1032, and the last location 64 watt, then 2 to the power of 6 bit. 6 bit. It's confusing, right? 6 bit. 1111 3 zeros. That is 30, right? Then you need to add everything. One like this. Confusing, right? So 7. The last one is 107. 7. 6F. Confusing, right? 6F. 6F. Then you are happy, right? Okay, to access, to write some data to here. Okay, this location. Next location 31, next one 32, last one 3F. Then happy, right? But that is not the case. You are supposed to use, that location to, write data. TX54. So what does that mean? That means internally, some hardware mechanism is implemented internally. Okay, something like FIFO, right? FIFO. Think about FIFO, first in, first out, right? FIFO. That means I would implement like this. I would implement internally hardware, right? I would design some head pointer and tail pointer. Initially, these two are the same. Don't do anything. These two are the same. 0, 0, for example. 0, 0, meaning it is pointing the first byte. The first byte. And if you execute first store byte instruction, then H will be written, right? And tail pointer will be incremented. Okay, tail pointer will be 1 now. Tail. Okay, and if you write one more character E, okay, and then tail pointer will be incremented to point next location. Then H, tail pointer will be incremented, something like this, right? And how about head pointer? Head pointer will be, incremented after sending out this, information. H, right? Send bit by bit, and that is the incremented. To take out second byte and send bit by bit. So you have to think about hardware implementation, right? So how FIFO is implemented, right? So that is a secret behind that, one location. Does it make sense? Any question? And in this example code, one more thing. In the example code, we are checking out what TX54 empty bit. Okay, TX54, is it empty? If it is empty, we are sending out first character, right? So we are sending out first character if it is empty. Then hardware will send out this character to your computer, right? Then after that guy is completely sent out, after. In other words, tx54 is empty again, then next character will be E. Hey, hello, right? HELLO. Next character will be written. Okay, and we are waiting until next character is completely sent out. Then tx54 is empty, then you are writing next character to FIFO. So in this implementation, in this program, we are just using 1 byte. We are not using actually this FIFO. Right? We are just using, we keep using, only one byte in, FIFO. Okay? So it is not good software implementation because we are not efficiently utilizing, 64, whole 64, FIFO. Anyway, for demonstration purpose. Okay. Okay, that is the one. Okay, 4 minutes left. Any question? No?
저 교수님 혹시 저번 과제 사과 관련해서 질문 하나 드려도 될까요?
Okay.
그 저번 수업 때 레퍼런스 코드를 저희가 봐서 하라고 하셨는데 혹시 그거를 공유해 주실 수 있나요?
Reference code? That
네네.
is included here, right? That is included. This example, hardware example, right? The Vivado example, it contains not only hardware but software as well, right? Software code, everything is here, right? So check out this.
네, 감사합니다.
Yeah, so download it. So you can browse through. Application, right? SQL application, source. Hello, I think this is the one. Yes, this is the one, right? So everything is included here, right? Like this, right? Yeah. Okay. Okay, any other questions? So we, yes.
헬로를 보낼 때요. 그 H 보낸 뒤에 그 H가 사라지는 건가요? 아니면 헤드 포인터가 1로 이동을 하는 건가요?
To send out H, right? Internally. Okay. You know what the best way to, so what do you think? The best way to understand IO device? What do you think? The best way to understand IO device? So UART. The best way to understand UART is, what do you think? Best way is design UART yourself. That is the best way. Design actual hardware by yourself. Everything will be clear, right? So the TX54, you write H, right? Then head pointer is here until you sent out H until sent out to notebook computer, right? And tail pointer will be incremented like this. So if you execute store byte instruction, then the data, say R2, R1, and R1 is E301030, right? The location, this FIFO location. Then the data, whatever the data is, let's say E, character E, okay, hello E will be written to the location where tail pointer is pointing, right? So E. Then how that character will be sent out? That is the question probably, right? What do you think? How would you send? That character is 48 in hex, right? 40 in 8 in ASCII code. That is H, right? And in binary, 0, 1, 0, 0, 1, 3 zeros. Okay. So you are supposed to send out D0, D1, data 1, D0, D1, D7. So from start bit, if you think about UART format, this format, the packet format, start bit, right? Start bit will be asserted like this. Start bit, I'm talking about this line. And D0, D0 is 0. That is D0, okay, which is 0. And then D1 is 0. Okay, D2 is 0. D3 is 1. D3 like this. Okay, and 0. Something like this, right? So that will be 0, 0, 0, 0, 0, 0, 0, okay, 0, 0, 1, 0, something like this. So from this data, how would you send bit by bit? What kind of hardware component would you use to implement that from this parallel 8-bit data to this bit by bit? We are talking about 1152 hertz, right? Himin, what do you think? What hardware component do you have to use? Any idea? Oh, that is digital design, I think. Digital design. Shifter, I think. Shift register. Do you remember? Shift register. Not shifter, shift register. Remember? Shift register. Let me open. Let me here. Shift register right here. Here I have slide, right? So send bit by bit, right? You are using this shift register. Okay. So D02, D7 in our UART case, right? D02, D7, that is loaded into flip-flops. These 8 flip-flops. And the data will be shifted out bit by bit. And clock, this clock is 1152. This clock, 1152. So using this shift register, you can send out this parallel, the parallel data, 8-bit data to, serial data, right? This parallel to serial, right? And then after sending out, using shift register, you are sending out bit by bit. Then after that, head pointer will be pointing. Head pointer will be pointing, this next character. Himin, is it answering your question?
네네, 감사합니다.
Okay. So again, best way to study IO device, hardware, design hardware yourself. Then everything will be clear, right? Everything will be clear, right? So if you design UART or timer, then probably very super easy to understand, super easy to read datasheet. I think that is fastest way to learn about IO devices, right? So if you have some experience, in IO device design, then the register access and internal mechanism, right? Things would be super, clear. Then, reading specification, okay, I understand. I can imagine, I can think of hardware mechanism behind the UART. Then, okay, one location for TX RX54. Okay, same location for TX RX54. No problem, right? I can differentiate these two. You can think yourself. Okay, and 64 by 54. Right? How come 64 byte, one location? Right, 54, right? So you head pointer, tail pointer, okay? That would be implemented in internally, right? In hardware. So, okay. Okay, I guess that's it. That's it for today. If you don't have any question. Okay, I'll talk to you. I'll see you next time. Okay, bye.
감사합니다.
Okay.
감사합니다.